Hello, we are looking at 2.11 logarithmic functions and characteristics. We start looking at logarithmic functions because they are the inverse of exponential functions. So to start, I actually want you to answer questions 1, 2, and 3, so the entire front page here on your own. So pause the video, answer those, and you can restart the video to see if your answers match with mine. All right, so I filled in my table. I did use my calculator for this. You could also do it without a calculator. And then for the inverse, I switched my x and my y, and then I rewrote my logarithmic form in exponential form. So I have 2 to the power of x, and I have my inputs and my outputs. For part 2, or question 2, we're looking at graphing them. And I graphed my logarithmic in blue and I labeled it, and then the exponential function in orange, and I also labeled that. They do look like inverses because we know for inverses they reflect across that line y equals x, and then at the bottom we have to figure out the domain and the range for both. So for number 3, since I have the graph available, whoops, we need to see the whole button there. I can see that my domain of my logarithmic function is from 0 to infinity because there is an asymptote here at 0. You could also rate it as x is greater than 0, and my range is all real numbers because this will go down forever and this will go up forever. So yes, it's going up gradually, but it'll still continue to rise. For my domain range of the inverse, which is the exponential function, we also know that our domain and range will flip the inverse, but we can see it in our graph. So our domain is all real numbers. It goes left forever. It'll go right forever. This will continue to get further and further to the right. My range is y is greater than 0 or 0 to infinity because there is an asymptote here for the x-axis. So at y equals 0. So let's go to the next page. So looking at number 4, we have graphs of 3 parent logarithmic functions shown, and we want to look at what do all of these graphs have in common. You can do this on your own, but I am going to walk through this one. Your answers might vary from mine. So I do notice 3 major things. All 3 of my graphs don't touch my y-axis. So I'm going to put that down. If it doesn't touch or cross my y-axis, that means I have a vertical asymptote at x equals 0. So I have a vertical asymptote at x equals 0. I also know that all my graphs are increasing. They are going up, but they're also increasing slowly. They're increasing and they're kind of leveling out. So we can say that they are increasing at a decreasing rate. And the last thing that stood out to me was all 3 of them cross the point right here at 1, 0. These are characteristics that we're going to talk about when we get to the quick notes section of these notes. So for part B, we need to identify which graph goes with which equation. So I'm going to start looking at log of x. I know that if there's not a base, there is an invisible base of 10. And so I want to see 10 to what exponent would give me an x value. So, well, 10 to the power of 1 gives me an x value of 10. So if it goes to the point 10 comma 1, that would be the graph for log of x. So looking here, 10 comma 1, is this dashed line. So I know log of x is the dashed. And if you want to explain why we have log base 10 of 10 equals 1, where this would be my x value, and then 1 is my y value, and it goes through that point. And I can do kind of that similar thing for the remaining two. So log base 4 of x, well, let's see here. I know that 4 to the power of 0.5, or 1/2, would give me an x value of 2. When I have an exponent of 1/2, that's the same thing as taking the square root. And so I want to see which graph goes through 2 comma 0.5. And I want to be careful because my scale is by 0.5, so it's not the dashed one. 0.5 is here, so that's going to be my dotted line because the dotted line goes through that point. And then we narrowed it down, which means my natural log is the solid line. A way that I can check that is I can kind of pick a point. If I choose an x value of 6, if I type in my calculator natural log of 6, so let's see what that gives us. I get about 1.8. And so looking at my graph, when my x value is 6, 1.8 is somewhere around here. That is in fact my solid line. So my natural log is that solid line. And we can say, and it goes through 6 comma about 1.8. So for number 5, suppose we shift our function to the right by 3 units. So we're going to think of our transformations here. If we're going right 3 units, that means we're going to have parentheses with a -3 on the inside, because we know in parentheses it's the opposite of what it looks. So if I were to write a new equation for g of x, I am so sorry. G of x is equal to, I still have my log base 4, but then I would have x minus 3 because I need this -3 to reflect the transformation of going right by 3 units. So how will that affect my characteristics? So my x-intercept, my asymptote, domain, and range. Well, my x-intercept will shift. If I'm shifting everything to the right, my original x-intercept was at 1. So looking back at the graph, I don't want to keep moving my paper up and down. So the first thing I'm going to say is my x-intercept will now be at 4 comma 0 instead of 1 comma 0. So if we go right 3, essentially adding 3 onto this one, which gives me that 4. My vertical asymptote originally was at x equals 0. Well, if I shift that to the right 3 units, it would be at 0. If I had a little graph here, it was here. And I go right 3, 1, 2, 3, my new vertical asymptote would be at an x value of 3. So my vertical asymptote will shift. So it'll shift 3 units to the right. So now it will be at x equals 3. My domain, originally my domain was from 0 to infinity, where the 0 was not included because of that vertical asymptote. So since it's shifting to the right, it'll now be at 3 comma infinity, or you could say x is greater than 3. Our range is based on our y values, how far down and how far up our graph goes. So if I'm just shifting my graph to the right, my range is actually going to be unchanged. My original range was all real numbers. Oops, sorry about that. And so if I'm moving it to the right, it will still be all real numbers. So let's look at a couple examples together on the other side after we do our quick notes. So in our quick notes, we're looking at some basic characteristics of logarithmic functions. So we have this graph is a type of logarithm. This specifically when our a value is greater than 0 and our base is bigger than 1. So a is in front of the log. And we have a vertical asymptote at x equals 0. So right here, I could kind of put some dotted lines in there. The graph on the right, when our a value is less than 0, but our b is still bigger than 1. If a is less than 0, our graph would be decreasing, and we still have a vertical asymptote at x equals 0. I want to add a little note here. These vertical asymptotes are at x equals 0 before any transformations. If we end up shifting our graph left or right, those vertical asymptotes will end up changing. When we're looking at logarithmic functions, they are always increasing or they are always decreasing. They never switch between the two, which means they will have no relative extrema. So no relative max or mins. The only like caveat to that is unless it's on a closed interval, then we might have something. And then for concavity, logarithmic functions are always concave up or they are always concave down. Similar to when we look at exponentials, they are always only concave up or only concave down, always increasing or always decreasing. If they never switch concavity, then they have no inflection points. When we're looking at end behavior, our ends, one of them is where the asymptote is. And so our end behavior on the left side, we would say the limit of our log function, and I'm just going to use like the template. So we would have a number in for A, number in for B. As x approaches 0 from the right, so from the positive x value side, and that can equal either positive or negative infinity. Those are your only two options for the left side of your graph. And then for the right side, we have our limit of that same log function. We would use the names so like f of x, g of x, h of x. And this is for the right side, so when x approaches positive infinity. And again, we only have two options. It could either be going towards positive infinity or negative infinity. So we're going to be filling in those, and we always want to make sure that our notation is correct when we're using limits for end behavior. So let's look at some examples. We have 4 examples to go through, and each one has a couple parts to them. So for example 1, it says write limit statements for the end behavior of the following logarithmic functions. So for part A, since we have the picture, that works out perfectly. So I'm going to make a little note just for this one. I'm not going to for the other two. For the left side, we're looking at the limit of f of x. We're going to use the name as x approaches 0 from the right. So as I put my pen on this, as we're going towards x value 0 of the right, I am going down. So I would say that that limit is approaching negative infinity. For the right side, my limit of f of x as x approaches positive infinity. So as my x values go more and more positive, my graph is going to the right, but it's also going up very gradually, but it's going up. And so we would say the right side is going towards positive infinity. As a reminder, you don't have to have the positive sign because it would still be understood as being positive, but I just want to include it here. I want you to do B on your own. So pause the video, and then when you restart it, you can check your answer. All right, so we have the limit of h of x as x approaches 0 from the right. As I'm going to it from the right, I'm going up, so that's positive infinity. And the limit of h of x as x approaches positive infinity. So as I go right more and more, arrow is going down, so that would be negative infinity. For part C, we don't have a graph, we just have an equation, but I notice a couple things about this. My a value right here is bigger than 0, and my base, my b, is bigger than 1. If my a value is bigger than 0, my graph will be increasing, so it might look something like this. And I would sketch it and use the sketch to help me write my limit notation for the end behavior. So now that I have a picture, I can see that the limit of g of x, because I still want to use the correct name, as x approaches 0 from the right, is going down, so that would be negative infinity. And the limit of g of x as x approaches positive infinity. So as I go further and further to the right, my arrow is going up and up and up, which would be positive infinity for that end behavior. So example 2, I am only going to do A and C. So for this one, it says for each of the following, determine if the logarithmic function is increasing or decreasing. So we have to include that. And if it is concave up or concave down. So for A, my graph is increasing, right? It is going up as I go to the right. So we're going to say increasing. And since it is increasing at a decreasing rate, it is concave down. So it's increasing, but it's slowing down. I could like continue this and it would look like concave down. So I'm going to say concave down. I'm going to leave B for you to do. And then for C, I will do this one. So I have my A value is -4. So my A value is less than 0. My B value is still bigger than 1. If my A value is less than 0, I know my graph is decreasing. I do like to sketch it out though. So it'll look like that. So it does look like part B. So we can say this is decreasing. And for the concavity, it is decreasing. It's super steep here, but then it gets less and less steep. So it's decreasing and slowing down or decreasing. And then this would end up being concave up because my like tangent lines or instantaneous rates of change are increasing because it's super negative here, less negative, almost getting to like a rate of change of 0. And so we say this is concave up, which your answer for C would actually match your answer for B. So same thing. So example 3 says write an equation for a logarithmic function that has a vertical asymptote at x equals -2 and goes through the point 7, 2. So my vertical asymptote at x equals -2 means that my graph shifted. Normally it's at x equals 0, so this means it actually moved to the left by 2 units. So when I think of my transformations, that means I'm going to have some parentheses, and I'm actually going to have a +2 on the inside of those parentheses because it moved to the left. And I have a point, I have an x value, and I have a y value. So I know it's a logarithmic function, so I can start this with log with some base. I don't want to assume what the base is. And I know that I'm going to have x plus 2 on the inside of parentheses, and that will equal my y value. So off to the side, if I take this logarithmic form and I change it into exponential form, I would have a base b, so a base b, to some exponent y, and that will equal my x plus 2. So we practiced that in 2.9. Now I have an x and a y value, so I can plug those in. So b squared, my value is 2, is equal to 7 plus 2. So b squared equals 9. Well, if b squared is 9, that means that my base has to be 3. So my base is going to be positive 3. So now I can write my formula. I have log base 3 of x plus 2 equals y. And that is my equation for the logarithmic function that has a vertical asymptote and goes through the point 7 comma 2. For the very last one, I'm going to look at part A and part C, and I'm going to leave B for you to do. So for part A, I have 2 times the log base 3 of x. So my A value is bigger than 0, so that means my graph will be increasing, and it'll look something like this. I don't have a horizontal translation, which means I still have a vertical asymptote at x equals 0. So I have an asymptote right on my axis. So my domain, I can write as x is greater than 0, or you could write it as 0 to infinity. And then my range, since it goes down forever and up forever, would be all real numbers, or I could write it as negative infinity to infinity. I'm going to leave B for you to try. I am going to go through C. So C is a little bit different because I have to factor out this 2. So thinking back to transformations, we have to have a positive 1 in front of x. So if I rewrite this, I'm going to actually rewrite it down here. So I still have that 8 out in front. I have log with my invisible base 10. I factor out the 2, and now I have x plus 3 halves. So that plus 3 halves means I am going to the left by 1.5 or 3 halves. So my domain is not going to be x is greater than 0. Since I'm going to the left, what happens to my graph is I have something that looks like this. And then I'm going to put a couple tick marks here. This point is going over 1.5 to the left. And so now I have a graph that looks like that. And so my range is still going to be all real numbers, but my domain is going to be x is greater than negative 3 halves. So I'll leave that for you to try, and then you still have your check for understanding on the other side.